Good morning, everyone. Welcome to this new webinar by the International Energy Agency in our program on energy data and modeling for Zambia. So today we will discuss a new session on energy modeling for long-term planning, and we will look at how to make projections on future energy demand, taking the building sector as an example. I will be joined by my colleagues Ariane and Tim, who are really experts in this field and who will share their perspective. So just to remind you where we are in our online course. So this is the second session on energy modeling. It will be followed by another one tomorrow on the power sector, and then we'll continue our path from demand transformation to supply, looking at the hydrocarbon sector. Just reminding you, as we are under this Zoom virtual format, any question you have, any need for clarification, please raise your hand. Otherwise, you can also ask questions in the Q&A box. We'll have a break session at the middle of today's webinar for Q&A, and also at the end. So today we will discuss taking the example of the building sector, but what we will discuss could be applied to other sectors like industry, like transport, like agriculture. And my colleagues will really take you through all the reasoning from looking at the activity, the structure, the performance of this end-use sector, the drivers related to them, and then all the process to estimate to go from final energy service demanded to the useful energy required, the allocation of fuels, of technologies, so that we can get an estimation of the final energy demand. For example, how much electricity will be consumed in the building sector for lighting in the coming years, how much oil will be required in the transport sector in the coming decades, etc. So before we start, I like that as we usually do, we kickstart this session with a few polling questions. So I invite you to go to menti.com, and I'm sharing the series of questions for today. So the code is 50080243. And the first question we are asking is, so looking at the residential sector in sub-Saharan Africa today, what do you think is the first fuel used in this sector after traditional biomass? We isolate traditional biomass because this is by far the number one, and it's weighting really a lot. Traditional biomass is used for cooking needs, and as you know, so depending on the country, but usually the majority of population still relies on the traditional use of biomass. It's really weighting a lot in the breakdown of fuels used. So after biomass, what would be the first fuel? Do you think it's electricity, oil, gas, coal, solar thermal? Can it be modern use of biomass with improved solutions, with fuels like biomass pellets, which are processed and which are much more efficient than the traditional use of firewood? So I give you a bit of time to think and answer. Okay, so thank you very much for your answers. What is striking is that we have very diverse answers, and that reflects the fact that in the residential sector, there are very different needs and there are very different fuels and type of energies who can meet these needs. So we can think of the need for lighting, the need for electric appliances, and this would require, of course, electricity. But when it comes to cooking, we can also have some gas with with methane or with local biodigesters who can enable cooking. There can also be some oil products like kerosene or like LPG, which are also a solution that helps cooking. In some countries, like China, coal is also a fuel that can be used in the residential sector for heating, air heating and house heating, or for cooking. When it comes to getting hot water for showering, for cleaning, solar thermal can be a very good solution, and it is very developed in places of the world like the Middle East, and there is a high potential in many places in the continent. So we really have a bouquet of different fuels providing different services, but the right answer to this question is that electricity is the number one fuel for sub-Saharan Africa after biomass, after traditional biomass in the residential sector. So you were right, rating electricity number one. So this was today's situation. Now, if we try to think of the future, in your opinion, what do you think will be the fuel that will grow most and account for the majority of final demand growth? And we are proposing the same fuels. Okay, thank you very much for your answers. So interestingly enough, we see that you also rate electricity number one as a fuel which is expected to grow most in the future. We'll see in a second what our different projections give, but we can see that oil and coal are very low in your opinion, and of course it will depend on what the future will be made of, what the policy choices will be. But indeed, when it comes to coal, if the policies are increasingly taking into account climate goals, there shall there will be very limited room for coal, especially in the residential sector, because there are many alternatives and cleaner and more efficient fuels to meet, for example, cooking needs or space heating needs. Okay, so thank you very, very much for your participation and your answers to those questions. I'm coming back to the presentation, and I just like to set the scene a bit more before handing the floor to Tim and Ariane, who will really enter into the building modeling lesson. But so just presenting some results of IEA modeling exercise on what the future could look like in the building. So here you have what you can see is the evolution in the world, so it's global, of energy demand in the building sector. So as we said, you can see that there is really a diverse mix of fuels which are used in the building sector, depending on what we need. Is it cooling? Is it heating? Is it powering appliances, etc.? And when we try to look at the future, this is a first projection according to the STEPS scenario, so stated policy scenario reflecting ongoing policy choices. And we would expect a strong increase of electricity share and electricity absolute value use in the energy demand. And let's say that the CO2 emissions would stagnate at their current level. But if we look in another scenario, which is our sustainable development scenario, aiming to reduce CO2 emissions and to get to net zero by the second half of the century, we see that there is a decrease in stabilization of energy demand for the building sector in the coming decades, and that the role of coal, the role of oil, and even of gas would be very much limited, while electricity would take the lion's share of energy demand in the building, since it would be more efficient and low and less intensive in terms of carbon emission. So this was the picture we anticipate in our calculation estimate for the world. If we look at sub-Saharan Africa, and here on the left side, you have the energy demand for the residential sector for oil and gas, and on the right, you have for electricity. So the latest historical data at the time of this exercise were 2018, and we can see that oil and gas were used a bit for lighting and appliances. This can be diesel for genset backup generators in places where the grid is not always reliable. Oil and gas were also used for water heating and cooking. So this can be LPG or kerosene. And when we look at electricity, it's of course mostly for lighting and appliances, but also for space cooling and a bit for water heating and cooking. So these are historical data. If we make projections under the STEPS scenario, what is striking is we expect a very high increase in energy demand in sub-Saharan Africa from the residential sector, coming from population growth, coming from urbanization, coming from increased consumption at household level, and oil and natural gas would really meet needs for cooking, especially with LPG. Electricity would enable to power more appliances and to meet lighting needs, as well as space cooling, which is expected to grow significantly. And this was the first modeling exercise under the STEPS scenario. If we look at the Africa case scenario, which is a normative modeling exercise where we say if we want by 2040 to have reached universal access to clean cooking and to electricity, if we want to have socioeconomic growth and a GDP growth as per the Africa Union 2063 agenda, if we want to limit air pollution, what should be the results by 2040 and what should be the pathway? So this is how the scenario is built. And here you can see the difference between STEPS, stated policy, and Africa case come from upward trends. For example, we have assumptions with higher GDP, we have assumption with universal access to cooking and to electricity, and this drives more energy demand. But we also have assumptions on efficiency, which contribute to limit the growth of energy demand. And so you can see that according to this scenario, energy demand from the residential sector would be expected to grow even further by 2040. Okay, I'm stopping here and giving the floor to Tim and Ariane, who will present you a bit more the rationale and really the mechanic and technically how do we do energy modeling projections when we try to estimate how the demand will evolve in a given sector, which is the building.
On this slide, you have the general schematic overview of the world energy model. And in this presentation, we will focus on the building sector, which includes the services and residential sector, which are encircled in red on the slide. You can also see the main driver of the related energy service demand. When looking at this overview, we should not forget that an important additional feedback needs to be considered: the impact that electricity and heat prices and fossil fuel prices have on end-use demand in general, and in this particular case, on the energy demand in the building sector. When working on the sector, the first step before doing any modeling is to analyze what do people want. What they want and use are called energy services. In the building sector, it can be space heating, cooling, lighting, cooking, etc. To meet service demand, we need energy, and this energy is consumed by different technologies. In the building sector, it can be air conditioners, light bulbs, radiators, etc. And for each equipment, we also have its associated efficiency. We therefore can distinguish three areas: activity, structure, and performance. The activity is linked to the energy services. The structure is linked to the type of equipment present in the building sector, and the performance is linked to the efficiencies of the different technologies. And all of this needs to be depicted in the model. If we look in more details at the structure of a building model, we see that we have different parts that make up the model. The first part includes all the inputs that are needed to do the modeling: historical data regarding energy balances, building stock, equipment sales, and also socioeconomic data like population, electrification rate, or GDP. And we also do some assumptions for the evolution of some of these data, so for instance, population. Some of these inputs will be used to compute energy service demand drivers, like household occupancy, floor area, or appliance ownership. Of course, these drivers will differ for each subsector. Indeed, the drivers are then used to determine the future useful energy demand, or the activity, as mentioned earlier. So for instance, for space heating, we can use the floor area as one of the drivers. In addition to that, we also need a number of historical and future technology data that describe the structure and performance of our system. These data include the efficiencies, the lifetime, the market share of the different technologies. We can then compute for each end use what technologies will meet the service demand, and we will finally estimate the energy demand by subsector and by fuel, as well as the investments and CO2 emissions. If we look in more details at the structure of a building model, we see that we have different parts that make up the model. The first part includes all the inputs that are needed to do the modeling. As we've just seen, we need a lot of data inputs, as data are essential for energy models. accurate balances are the basis for all modeling work, as we have seen and mentioned in the previous webinars on energy statistics. That's why it's important to build a data repository to organize all the data that you will use for your modeling. As mentioned, the data include energy balances, technologies data with efficiencies, costs, but also policy data that will impact the evolution of this sector. We will explore which are the most important ones in the next slides. As mentioned earlier, one important step of the modeling process is to define energy demand drivers, as they play a key role in describing energy consumption patterns in energy models. Thus, it's crucial to define the best proxy to describe past trends and possible future ones. Before looking in detail at drivers and different methodologies to estimate them, you can see here the general structure for modeling end-use sectors. So first, with the drivers and econometric analysis, we estimate the evolution of the energy service demand, or useful energy. Then, to meet the service demand, we allocate different technologies. And in the case of the world energy model, we use a cost-based approach to do this. Then, with the efficiencies of the different technologies, we can compute the final energy demand. If we go back to the drivers, we will look over the next slides at possible methodologies to identify the best proxy for each subsector. The projections of activity variables can be based on regression with respect to GDP or electrification, but we can also use different types of curves, like the S-curve. And as mentioned earlier, this requires to use different data that can come from the IMF or other national reports.
You've now been introduced to the importance of buildings energy demand modelling and the strong role of bottom-up modelling of energy demand for each end use within the building sector. And then following this, the processes and structure used in the modelling of buildings energy demand in the International Energy Agency. And now I'd like to focus in on one of the most important steps of our modelling process, and that is the definition of the best proxy to then describe the activity variable that can help us understand how service demand evolves for each type of building end use. So again, the proxy is the link that helps us to go from socioeconomic information to activity variables and then to services demand. Now, why do we need this link? Well, firstly, activity variables, we might have this information available for certain countries in the historical period, but we don't have it available for all countries over all of the time series, and we definitely don't have this information available for the projections. So therefore, it's up to us to take the information that we do have, and that is socio-economic information, and to use this information and these assumptions for the future to calculate our own activity variables. Once we've calculated these activity variables, we can use them in our projections to understand how service demand evolves, and then based on what technologies we choose, how energy demand evolves in our projections. Now, there are several types of activity variables that are of interest to us. Certainly in the building sector, one of the most important activity variables is household occupancy. So this is how many people live in each household on average. Now, household occupancy can help us to understand energy demand for end uses such as cooking or water heating, for example. Now, because we do not have information on household occupancy into the future, it's up to us to try and define a relationship between a variable that we do have information in the future and this household occupancy variable. So here we've chosen to plot values of household income against household occupancy. So we've taken all the data on household occupancy that we do have for historical periods for different countries, and we've put them on this chart against the GNI per capita, which is in itself an indicator of household income or of personal income. And what we can see is we have an inverse curve that's being drawn here. So that means that as we increase the average income per capita or per household, then we are decreasing the number of people per household. So here we're seeing a strong relationship between GNI per capita, so gross national income per capita, and a decreasing number of people per household. So we have on the right an inverse curve equation that can be used to define this relationship, and then can be very interesting for us and is a key step in our modeling to be able to say in the future, if from our external assumptions, which for us come from organizations such as the International Monetary Fund, the World Bank, and our own assessment and projections of economic growth and population, we then use these assumptions on economic variables to understand via this equation how household occupancy evolves in time. So that's just one example of this process of identifying a proxy that has a good relationship with the variable that interests us and using this proxy to describe the activity variable. So here, household occupancy. Now, another example of a relationship of interest to us in the buildings energy demand modeling area is ownership variables. And so how does the ownership of a given appliance, such as a refrigerator in this example, evolve in time based on another variable? So here we've plotted ownership of refrigerators for all the countries for which we have data and over all the years for which we have data. And we've plotted that against here where we have a discriminant criterion, but we can very easily say that we can plot this against GNI per capita or even GDP per capita. So the most important variable to have on the x-axis is income in this case. And if we build this chart and fill out the data, we can very clearly see that there is an S-curve relationship between refrigeration ownership, so the average number of refrigerators per household, and the average income. And so that means that with time, as income increases, then we get to a point where the number of refrigerators on average per household starts to really increase. And then as we get to a point where households are increasingly rich, then the growth in refrigerator ownership slows down. Because once we get to a point where we already have at least one refrigerator on average per household, then obviously there's less need to increase and to continue to purchase additional refrigerators. So there is a saturation point, and that's why S-curves are so important, because they show us at the start that we might not have enough income even to think about buying a refrigerator, but at a certain point we start to cross that threshold and a refrigerator becomes a desirable and useful purchase and use of income. So we see that growth, that increase in the rate of growth of the S-curve, and then it flattens out as we start to saturate. So the S-curve is a very important indicator for understanding the relationship between many economic variables and the activity variables that interest us for buildings energy demand modeling. And I'll get to a description of the discriminant criterion and how we can draw upon several economic variables to influence and describe this curve in just a minute. But firstly, I would like to go through an example of air conditioning ownership. So here we've done the same thing as in the previous figure. We've plotted on the left-hand side, on the y-axis, the average ownership of air conditioners, and on the x-axis, the average income per capita. So we've used all the data points that we have in our database, and we can see that it's a big cloud of points without a very strong relationship. So here it's difficult to imagine an S-curve describing the evolution of air conditioner ownership with income. But when we bring an additional piece of information to the picture, we start to see much clearer relationships. So now we start to plot data points, so air conditioner ownership and income, depending on the need for cooling in that region. So here the need for cooling is described in terms of annual cooling degree days. So a cooling degree day is a variable that can be calculated based on the threshold temperature in a given country and the average daily temperatures within that country. So here we can clearly see that for countries in darkest red, so the countries with the greatest cooling demand need, there is a relatively strong view of an S-curve that evolves in time. So we can see that as in those countries incomes start to increase, the rate of air conditioner ownership rapidly increases and moves towards 1, so an average of 1 air conditioner per household. However, if we look at countries in blue, so with very low cooling needs, then we can see that even when incomes, average per capita incomes increase to very high levels, the air conditioner ownership stays quite low. Because obviously these households, despite their high incomes, are prioritizing purchases in other needs because their cooling needs are not very high and not very pressing. So the message here is that sometimes we might have just the economic variable, so GDP per capita, and some information on ownership, but that's not enough to define a clear trend and a clear curve that can be useful for us. So sometimes we need to bring additional data to the table to help us understand the evolution and the relationship between the economic variable and the activity variable that interests us. Now, before going on, I'd just like to summarize some of the key end uses that we model in a bottom-up fashion in our buildings energy demand modeling, and the activity variables that we use to describe the energy service demand for that end use. And then further on, the proxy that we use, so the economic variable that is a key variable for us to help to understand the relationship between evolving economic conditions and the activity variable. And then finally on the right, the type of curve and the type of equation that we use to connect the proxy with the activity variable. So firstly, with cooking, the first curve that we saw was an inverse curve. And so for cooking, we use people per household to help us understand the evolution of service demand. So people per household is our activity variable. And as with all end uses in buildings, we're using GNI per capita, or you can use GDP per capita as well, as the most important proxy to help us describe the evolution of the activity variable. So we take our projection of GNI per capita that comes from other assumptions. So again, it might be World Bank, IMF. For population, it might be the United Nations. And then we use this variable via the curve, so the inverse curve in this case for cooking, to describe people per household and understand the evolution of people per household in time. For lighting, we use an S-curve because the activity variable is floor space per household. And with an S-curve, that describes the fact that as households become more rich, so does the floor space of those households increase, and then we get to a point where there's saturation, and so the S-curve starts to flatten out. For water heating, it's again a question of describing energy service demand by the number of people that live in the household, because if we think that each person in the household may take 1 shower per day, therefore the energy demand need for water heating is dependent on the number of people in the household. So here, again, we're using an inverse curve, the same as for cooking. But then if we look at air conditioning, so cooling and appliances, then it's a question of ownership. How many air conditioners or how many refrigerators, televisions are owned on average by the household? And then how does this ownership evolve based on increasing income? So again, an S-curve, rapidly increasing at a certain point and then starting to slow down as ownership saturates. Now, just a note here on cooling, we could also say that floor space per household is an important variable, because if we're trying to cool a much larger household with 1 air conditioner, then we're going to be having a higher energy service demand. So we can certainly look at both variables, firstly the ownership rate, and then also if we have an increasing number of meters squared per household, that will also increase the floor space, the energy service demand, sorry. So in cases like this, we can look at having 2 activity variables that both combined can help us to understand the evolution of energy service demand. Now, to move on, I wanted to come back to the fact that sometimes we want to bring in additional variables to help us describe the trends. So if we look on the left-hand figure, the x-axis here is just GNI per capita. So it's an income proxy essentially. So we're taking our income variable and we're using this to describe the number of units per household. But we can see that the curve is quite cramped. It's really not an easily defined S-curve. And that's because in the first, let's say, $5,000 of GNI per capita, there's a huge amount of people that suddenly buy refrigerators. And it's all happening very rapidly, and perhaps economic variables such as GNI per capita are not the perfect variable to understand what's happening in this first part of the curve. But now if we turn to the right-hand side figure, then we can we use here a discriminant criterion. So this is basically saying it's a variable without a unit, which is just an indicator that combines several proxies. So it's combining GNI per capita, so it's taking the economic variable, but we're also bringing in information on the electrification rate within the country and the urbanization rate. Because when we start plotting this data, we clearly see that not only does the economic variable influence ownership, but so does electrification rate and urbanization. Because obviously we're not going to buy a refrigerator if we do not have access to electricity. So despite the fact that we might have an income, if without electricity, there's no point buying a refrigerator. So this is, it seems evident, but obviously it becomes very important when we start translating it into these curves, and we can see this flat period at the beginning for those that still don't have access to electricity, despite the fact that they might have an income. And likewise, the data shows that with higher levels of urbanization, we also have higher levels of refrigerator ownership. And so we bring in these three different variables that describe so an energy access trend, an economic trend, and a geographical trend, and bring that information together to build this discriminant criterion, which then helps us to get a much more clearly defined S-curve, which is then more useful in understanding in the future with a given a value for energy access, for income, and for urbanization, what might we expect in terms of ownership. So this is multivariate analysis and multivariate regression, as opposed to the earlier examples which were shown, which were using a single variable, so GDP per capita in those instances. Okay, now let's run through the principles of multivariate analysis for using many or several economic variables, population variables, or other interesting variables for which we have information to describe the evolution of activity variables. So the first point here is to look at the data that we do have. So taking the data we have on, say, if we're interested in refrigeration ownership, looking at the available data on refrigeration ownership, selecting a set of these data points which seem like a good, clean trend, and then trying to match these data points with available variable data on, say, GNI per capita, GNI absolute values, electrification rates, weather data perhaps, or any other variables that might be available. And then what we can do is plot all these variables together on a chart. And so, for instance, we'll have our variables on the y-axis on refrigeration ownership, and then we'll be plotting that on the x-axis against lots of different variables again and again to try and understand, is there a relationship between that variable refrigeration ownership and the variable that we're putting on the x-axis. And so what we can do, what we achieve by doing this, is we identify the most important variables that seem to have some sort of relationship between this variable and refrigeration ownership. And then we can partition the data into similarities, or based on what the data is actually describing. So for instance, if I take GDP per capita or GNI per capita, they're very similar data points. And so within this multivariate process, there's no point having data points that overlap and describe very similar trends. So even though both GNI per capita and GDP per capita are very useful variables that can both be used to describe the evolution of my activity variable, I'm not going to put them both into this multivariate analysis because they are describing the same things. However, if we look at a variable such as electricity access, then that is removed from GDP per capita and describing a different set of trends, and therefore we would put that in another class, and it would be very useful then to have variables from different classes, for instance 2 or 3 variables from 2 or 3 different classes, and bring these together to then feed into to establish the best combination of these descriptive variables that can be used to describe our activity variable. So once we have the 3 or the 2 variables that we've chosen, then we want to use a certain type of multivariate regression to understand what the best combination of these variables is to best describe this activity variable trend. So for us, we use canonical variate analysis. And so that's something that that you can look up and try and understand the processes involved, or there's many other multivariate regression techniques that can be used to combine several variables to deliver one discriminant criteria, so one variable that combines all this information and then can be used for us to plot and understand the evolution of the activity variable. So that's then step 5. Once we have this relationship defined, then we can use our projections of, say, electricity access rates, of urbanization, of GDP per capita, feed all this information in, calculate our discriminant criteria, then take the discriminant criteria, put it into our curve equation, so our S-curve equation in this case, and then that will give us a forecast of the ownership of the activity variable. Now, the final point I want to make before I pass on again here is what we do with tracking data and how do we project the variables that interest us when we do not have the available historical data. So to take a step back, the first thing we do is we bring all the data that we do have together for all the countries that interest us. And then what we'll do, we'll divide the countries into different classes based on the type of, I guess, the category of the country. And so, for instance, we would bring countries together that have similar economic contexts, that have similar climatic and population growth contexts. So here on the left, we can see we've put countries, so country A, B, and C into different classes. And so we have several different classes for countries across the world. But for instance, if you're looking just at the African region, it might be pertinent just to have one class and to not bother about defining different classes. Now, once we've done that classification by class, then we need to look at the data availability for each country within each class. So for instance, if we take the example of country A, then country A is a country that is well informed in terms of data. So we have historical data available for many years for the activity variable that interests us. So it could be household occupancy, it could be refrigeration ownership rates, it could be floor area per average household. So here we have the information we need historically to be able to build the curve, build a robust equation that then can be used for the projections. However, for many countries, this unfortunately isn't the case. We do not have this data available. So for many countries, we find ourselves in the position of country B. So that means we're poorly informed. We might only have a couple of data points. So there might be a data point from a survey that's taken place only once, or maybe 5 years ago and 10 years before that. And so that means that we don't have sufficient data available to build a robust and reliable curve, so an S-curve equation, for example, and then to be able to use this S-curve equation to project activity variables into the future. And so what we do in this case is we use the curve that was described by all the countries for which we do have data. So we take the average curve of all the countries in class 3. So for instance, if we put all the data for ownership of refrigerators for countries in class 3 together in one figure, and then we use that to describe, to build an S-curve, and we have the equation for that S-curve, we can then use that S-curve equation for all countries that find themselves in the position of country B. But we shouldn't forget that for country B, we do have 1 or 2 data points. So what we'll do is we'll shift the curve up or down to make sure that the curve is running through the most recent historical data point that we have available. So that's a way of ensuring that for us, we can use these curves to describe the trends for the 1 or 2 data points we do have, and to backfill the missing historical data, as well as understanding how these activity variables will evolve in the future. The final situation is the situation of country C. So this is a country for which we have no data at all for activity variables for the end use that interests us. So in this case, we have no other options. All we can do is take the average curve of class 3, so the average of all the countries within this class. And so that means country C will just be described by the average throughout, because we don't have any data points to be able to shift and run through those data points. And so we go straight through to the projections of the activity variables using obviously the economic variables that are specific to country C, but using the S-curve or the inverse curve equation, that is the average of all the countries in class 3. So this is a very important point on how to find the data, and then what to do with the data, and what to do, very importantly, when we don't have the data, all the data that we need to build these curves, and therefore to project the activity variables. And just a point to note on data, so obviously there's many different sources available for countries across the world, but in many African countries it can be quite difficult to find this sort of data. So at the International Energy Agency, we've often looked to surveys such as the surveys conducted by USAID, and we can find these surveys online, the DHS surveys, and often there is information within those surveys that can be used to help us in this modeling process. Alternatively, there can be specific literature on a specific country based on surveys conducted within that country, or based on academic work. But basically, the first step certainly is to look for the data that does exist for the end users that interest us most, and to contact or reach out to as many people as you can to try and get the best data and ensure that you start with the strongest foundation.
Okay, so I'm coming back to the presentation, and happy to take some questions. We received a few very interesting one. I'll try to start addressing them, and in the last part of this session, we will have Ariane joining us as well, and she will be able to provide more insights. So one first question is, how is the stochastic nature of household occupancy treated in the context of sub-Saharan Africa, with possibilities of larger families? So this is an excellent question, because what we've presented so far were only referring to average household occupancy, and in our own modeling exercise, depending on where we look, sometimes if we lack data, we'd have no other choice to take just national average. In the case of our recent Africa Energy Outlook analysis, what we have done is to break down urban versus rural settlements, and to, when available, to take some different assumptions and data for number of people per household, whether you are in an urban context or in a rural context. But as always, the more input data you get, the more accurate you can be in your projection and in your modeling exercise. So there is another question that might refer more to the specifically the building sector, and the building material that can contribute to energy savings. So Mr. Joshua is referring to passive house or to net zero buildings, and the question is, how can we take into account this in the modeling exercise? So I'll answer very quickly, and Ariane might be able to provide more details. But As you may have seen in the Excel exercise, we, for example, if we want to anticipate how the need for cooling will evolve, we have made many simplification just looking at the cooling needs as expressed as intensity of service, and we have taken some assumptions on the standard growth of this, not looking too much into the cooling degree days, so the real weather that for which we can have projection, because there are some models that can give the evolution of climate and of what should be the average temperatures per region. So this is a key input that will of course impact the needs for cooling in the building sectors. And then of course building design with passive houses can definitely be part of the answer to these cooling needs. The only fact of painting sometimes the walls in white rather than in dark can have really an impact in the average temperature in the house given the sun irradiation. So there are many other elements that we can take into account in the modeling. Again, it's a question of how accurate we want to be, what are the available input data we can rely on. But definitely, it's not only about the air conditioning units service intensity. It's about the external temperature, weather, and it's about how the house is reacting to this weather, and are the other ways to have a house keeping you more in a cold or in a cool atmosphere, for example. And then you are also mentioning some net zero or even positive buildings. Indeed, in some developing countries, you have that kind of projects with buildings who are able to be totally autonomous, producing their own electricity with solar PV in the rooftop, for example, or with small geothermal installation. There could be some natural cooling in the design of the building, making the most of the wind, of this passive heating or passive cooling. So indeed, there is a lot of innovation, and buildings are increasingly more energy efficient as well. The last question on the energy indicators that should be, how can they be applicable to rural sub-Saharan Africa? I will let it to Ariane to explain a bit more at what point of the reasoning we take into account this rural sub-Saharan African context with low rates of access to electricity. But of course, this is part of the exercise, and we're aiming to taking it into account. So we have another question on the data source for surveys, as it was mentioned by Tim that we can look at the USAID survey, and we often hear about those surveys. So indeed, we can question ourselves why make them attractive. And it's indeed some surveys which are done on a quite regular base between every 3 to every 5 years in a country. They are consistent. They are mostly consistent across countries, so you can have comparability between the results in country A and country B. They are usually quite consistent over time, so you can have comparability between what you measured 5 years ago and what you are measuring today. So this is one of the most deployed survey in developing countries. So it's an important source. There are many others. We can refer to WHO survey too, who will run those DHS type of survey. But what we usually try to make the most of any source of data. The key parameters to look at is again what's the scope, what's the design of the survey? Can we have comparability across countries? And over time, with this type of surveying tool. So thank you very much for this question. I propose we go to the second part of the presentation, and we'll have more time for questions at the end. But before that, I would just like to ask you 2 more questions. So I invite you to go back to the Menti application. So we are still with the same code. So if you did not unplug, you shall be able to see the new question appearing. If not, I just remind you the code. It's 50080243. And here the question is more about an exercise. If we know the energy consumption of an air conditioner unit, what is the most important parameter that we need if we want to estimate total demand? So is it floor space? Is it number of household? Is it number of units per household? Okay, so we are receiving some answers. Thanks a lot. Most of you are voting for this floor space and then number of units per household. So in the case of estimating future energy demand for cooling needs at a country level, we could need all of those variables, and you will have seen in the exercise that we are taking into account a number of them. Maybe to keep yes, so we would need all those variables at different step of the calculation. Floor space is an important indicator to understand what the need for cooling would be. The highest, the biggest the house, the more cooling will be required. This can also be reflected in the number of units of AC units per household. And of course, once you have done estimation at an average household level, you will need the number of household just to multiply and to get the number at the country level. So there is no bad answer. All those parameters are very important to make this kind of calculation. Now, if we look to the need for hot water at home, assuming that we know the energy consumption of a water heater in a household, what would be the most important parameter to estimate the total energy demand for water heating? Okay, well, I'll go very quickly on that because it's quite obvious that floor space is not a very relevant parameter, but because regardless to the size of your house, you might take only one, or you will take one shower a day. So it will mostly depend on number of people living here, and then number of population and number of household in the country. So thanks a lot for your answer to that. So we'll now move to the second part of the session, looking really how step by step we move from the need for energy service to what will be the fuel and technology required to meet this demand, and finding what will be then the need for final energy demand. And last, Tim will share some findings on the building sector. So I'm giving back the floor to them.
Once we have determined past and projected activity variables and service demand intensity, the total energy service demand, or useful energy, can be computed. For this, we can rely on end-use intensity, which is derived from our projections of activity drivers, as well as other data coming from our database, like the historic energy demand by fuel and end users, historic and projected temperatures. So we usually use heating degree days and cooling degree days, or historical technology market share and efficiency. For instance, with all this information, we can compute the energy intensity per square meter for space heating. Once obtained, the total projected service demand, we can now reflect on which technologies will meet the demand. So for each year of the projection, we can compute the total energy service demand that needs to be satisfied by new equipment, by accounting for new incremental demand and considering the retirement of existing technologies. So of course, in later years of the projection, we also have to take into account the retirement of technologies that were added by our model. So how do we do this? For this, we need to have a detailed stock accounting. So with the historical market shares and efficiencies, we can compute the stock of existing technologies. And with the lifetime, we can determine the remaining stock for each year of our projection. And finally, we can compute the service demand to be met with new sales. So the sales of new equipment need therefore to replace previous equipment and to meet new demand for energy services. So you can see that the lifetime of equipment and its age distribution can play an important role in the capability of the system to renew the overall technology stock. In countries with burgeoning energy demand, such as in developing countries, the share of replacing old infrastructure and technologies is more limited, while its weight is more important in advanced economies. Now we have to determine which technologies will meet the service demand. The technology and fuel choice depends on a variety of elements, and first of all, on the available technologies for each subsector in each market considered. That's why we have an important database with all technologies available in each subsector. So for instance, you can look at the cooling subsector and you can see the different types of air conditioner that are in the model. The choice of technology depends on various parameters. The available potential of renewable resources can play a very important role, as well as several energy policies, such as energy efficiency standards. In the World Energy Model, we rely mainly on a cost-based approach to determine which technologies will be installed. For this, we need to compute the cost associated to each technology, which includes the investment cost as well as the operation cost. For instance, for an air conditioner, we must take into account the price of this AC, but also the price of electricity that will be consumed by this technology. In our model, we assume that the technology share will be proportional to 1 divided by the specific cost of this technology. This least cost approach is often the most used criterion to select the technologies, but it's also important to consider boundaries to reflect market failures, behavioral patterns, and energy policies. For instance, we can set a minimum target for heat pump to be installed if we consider that energy policies are pushing the development. Here you have an example of the projections we made for various lighting technologies. On the left, you have the evolution of efficiencies, and on the right, the evolution of the market share of the LED. So with this information, we'll be able to compute the main outputs of the model. So you can see that estimates of historical efficiencies and performances of equipment and possible future evolutions are key parameters to make reliable estimates. That's why technology partnership, sharing information, and continuous interaction with the energy industry are really crucial elements to achieve it. As said before, once the technology choice is determined for each subsector for each projection year, together with the market share, efficiency, and fuel of use, the final energy demand can be computed, as well as the related CO2 emissions and the investments that are needed for new equipment additions.
In the last part of this building's energy demand modelling session, I would like to provide several examples of the results of our modelling, specifically the results of our modelling applied to the Africa context, and use these results to reinforce the importance of efficiency gains and understanding the impacts of improving efficiency and changing technologies on energy demand. So these are some of the results that we can then communicate to policymakers to reinforce certain messages and the importance of taking steps and putting in place policies to achieve energy objectives. So here we've taken an example from the International Energy Agency's World Energy Outlook Special Report on Africa, published in 2019. So looking at electricity demand from household appliances in the year 2040 under two different scenarios. Now, if we look at the left part of the figure, we can see that under a scenario where the current and announced policies are enacted and economic growth follows an expected trajectory as announced by the International Monetary Fund, then we can see electricity demand across Africa for these uses, for residential uses, increasing to around 350 or close to 400 terawatt hours. However, if we pass to a scenario where economic growth in Africa is much more rapid, so economic growth is in line with the expectations for African countries, and we also have energy access, so universal access to electricity and to clean cooking, which is achieved by 2030, so in line with the Sustainable Development Goals, then we see a much more rapid growth in energy service demand. So obviously, if we come back to the activity variable story and the bottom-up modeling process, then higher economic activity means higher average household incomes. This then translates to greater floor area on average per household, much higher household ownership of appliances such as refrigerators, televisions, washing machines, and higher household ownership of cooling equipment such as air conditioners. So if we just added to the system the same equipment that was being used in the STEP scenario, then we would have a huge increase in electricity demand. So going from around 350 terawatt hours to over 1,000 terawatt hours. So this obviously has very important implications for power systems and for the costs needed to increase generation capacity, increase transmission capacity, and then for energy bills, electricity bills for consumers. But what we want to show here is that by improving the efficiency of the appliances that are added, we can drastically reduce the impact of all these additional appliances. So that means that we can have big increase in demand for energy services, and so in quality of life because people have more appliances, but we've limited the impact on the energy system. So that's through greater efficiency. And so if we look at the right-hand side of the figure, we can see that the ownership variables for different types of appliances averaged across Africa. So we can see that we have significant growth already in the steppes, especially in appliances such as televisions and refrigerators, but also in air conditioners, although they do remain at a much lower base. However, if we look at the Africa case, then this growth in ownership really does explode. So obviously this is important. It's people getting access to services, but via the modeling, we understand that as we put in place more efficient technologies, so thanks to policies, then we can limit the impact on energy systems of this increase in energy demand, energy service demand. So to be able to do this sort of analysis, we also need to have the modeling in place, but we need to understand what policies are in place today and what are the efficiencies of existing equipment and equipment being sold. For instance, we'll need to know how efficient are the air conditioners being sold today and what policies are in place that would impact the efficiency of these air conditioners. So that provides us with a baseline, and we can also look at how the policies and the policy change over the last years has impacted the energy intensity of these end users. So here is just an example where both heating and cooling policies have been tracked, and we can look at the building stock and the useful energy demand in terms of understanding which part of that energy demand is covered by policies or not covered by policies. And then based on that, we can understand how stringent is the average coverage across the building stock. And so what we want to see is that the stringency improvement really brings down the energy intensity of meeting demand for services such as cooling and heating. And if we take the example of water heating, then here we're looking at the evolution of energy demand in 3 different scenarios. So the first scenario, the RTS, is a scenario similar to STEP. So here we're just looking at the policies that are in place and the policies that have been announced, whereas the 2 scenarios to the right are more ambitious scenarios that meet climate objectives, so a 2-degree scenario and a below 2-degree scenario. So what we see here is just pure outputs of our model when we impose the constraints of saying we need to reduce emissions in line with a certain scenario, so 2 degrees or beyond 2 degrees. Then that means we need to see a big change in the fuel mix. And so this is obviously bottom up. It's coming from us saying we need to allocate a renewable technology as opposed to a fossil fuel fired technology. And these are the evolutions of the energy mix that then result. So it's these kind of results that can provide a visual communication of what the modeling is doing and then help us to bring together key messages and key numbers to communicate to the policymakers who can then act on the information coming from the model. And one final slide here is very specific to Africa and specific to cooling to again underline the importance of increasing efficiency. So Africa's cooling needs, as many of us know, are much higher than most other places in the rest of the world. Many locations across Africa have cooling needs that are an order of magnitude higher than in countries such as France or Italy. And these cooling needs also dwarf major cooling demand centers of China and the United States today. And we see that almost 700 million Africans today live in areas where the average daily temperature exceeds 25 degrees. And average temperatures are often 1 to 2 degrees higher again in cities. And as Africa's population increasingly urbanizes, cooling needs will further grow. By 2040, the number of Africans living in hot areas approaches 1.2 billion people. As populations expand, especially in cities, and average temperatures increase with climate change. High cooling needs today and higher cooling needs tomorrow contrast with some of the lowest levels of air conditioner ownership in any region. Averaging today only 6 units, so 6 air conditioners on average per 100 households. Now, obviously, wealthier countries across the continent, such as Morocco, Algeria, and Tunisia, have higher ownership rates that can be up to 3 times the average of the African continent itself, while less affluent countries with often much higher cooling needs have ownership levels that are only half the African average or less. So as a consequence of this low average ownership of cooling needs, electricity demand for cooling today is very, very low in Africa. But the potential for future growth is strong. Ownership of cooling devices sees an important increase in our Africa case in response to these higher average incomes I described earlier and rates of access to electricity. So we reach in 2040 an average of 25 units per 100 households, but this is still well below the global average today. Ownership of fans increases further, but fans obviously have a lesser impact on electricity demand. So if we focus on electricity demand from air conditioners, then we can see that electricity demand in the residential sector across Africa for this end use could grow to well over 200 terawatt hours by 2040. So that is just a huge increase in demand that would have the day, so difficult to manage. But the importance here is to use the building energy demand modeling to understand that if we change the efficiency of these air conditioners, then we have the potential to cut this future growth in half. So we can reduce costs for the power system, reduce costs for the consumer, and reduce emissions. So here, this is again the messaging using the model to understand if we change certain variables, such as putting in place a policy which improves air conditioner efficiency, what are the results that we could expect?
Okay, so I would like now to come to the Excel exercise we have just that you have received, and that was aiming at presenting a case for energy demand for residential cooling. So we'll start with this exercise, and in a few minutes, Ariane will join us again to address your more accurate questions on the building sector. So coming to the exercise. Okay, so you were given a model, and the case we were in is that we want to estimate what the future energy demand for residential cooling will be. And for that, sorry, I will zoom in. You were given, as always, some drivers, including socioeconomic information, but also information related to the specific residential sector, like number of household, and to the cooling needs, like current number of AC units. And then what we will do is exactly what we discussed in the presentation, looking at the ownership rate of AC units to have an estimation of the number of AC units in the country. We will look at the energy service demand in the country, so the intensity people want to get some cooling services, efficiency levels of each of the technologies, allocation of those technologies, so market share of the different type of AC units or other devices that can provide cooling. And after all those steps, we'll be able to deduct what the future electricity, the final electricity demand will be from residential sector for cooling. And looking at the columns, we have some historical data. We will need to make some first calculation on what was the situation so far, and then we will be able, based on those historical data, to make some projections. So I coming back to the sheet with questions. So you were first asked to recompute some historical indicators that we will use in our calculation. So I think we were given GDP per capita in USD, and we wanted to get some kilo USD for simplicity and to be able to make easier calculation. So this is quite an easy calculation, going from USD to kilo USD. Then also you were given the number of AC units in the country that could come from data collected from specific collections, like custom imports of products or surveys. But in that case, you were given the historical data, and we wanted to get estimation of the number of AC units per household, since we will think at the household level. And then the question, once we have those indicators from the historical data, we want to make projections of the drivers. And as it was explained by Tim, if we don't know how the number of AC units per household will evolve in the future, but we can try to. But we know how the GDP per capita would evolve based on projections made by International Monetary Fund, for example. So we can try to find a relation between how the ownership rate of AC units relates to income of household and GDP per capita. And this is exactly what was presented by Tim. And there are different ways of doing it. So here you can see that in the year 2000 we had 40 AC units per thousand household. This number raised to 62 AC units per thousand households in 2018. How will that evolve? There are different ways of doing it. The first and easiest one is just to look at what has been the growth rate in the past. So we can just calculate a compound average growth rate. And in that case, we thought that uh, we have on average a 2.5% increase year after year. So we could say, okay, let's just use the same, let's just apply the same growth rate in the future. This is the most simplified and basic approach. What we can do, as just mentioned, is try to see if there is any relation between how GDP per capita has evolved in the past and how number of units per household have evolved. And in that case, this is an econometric approach. What we've done is to put on the chart those two variables, so AC units per household on the left and income on the right, and we can see there is quite a linear relation. So we can deduct a formula which is expressed as y equals a constant a multiplied by x, the other variable, plus b, and then with Excel we can just make appear we can just explicit the formula parameters, and based on this trend line apply it to the future. So this is a first way of doing it. So the reasoning is we don't know how number of AC units per household will evolve, but we know how GDP per capita is to evolve, and we know how those two variables are connected with a direct line. So this way we could have our projections of AC units per household. When it comes to number of person per household, this here we also have historical data. How will this evolve? Again, we can try to look at how this evolved in the past, or we can also try to find a relation between how GDP per capita is evolving and how number of people per household is evolving in the past in this country, or looking at other countries with a similar profile. And here we don't have a line which is as linear and as simple as what we had before. We have an inverse curve, so the mathematical formula is a bit more complex. We have three parameters, A, B, B, C, and using Excel functionality, which is the solver, we can find what those parameters are, and based on historical relation, project this how this would evolve in the future. So this being done, we can get the number of, we just got the number of AC units per household, and we are getting the number of people per household. We can deduct a number of households since we have this population estimation, and we can, most importantly, have a projection of how many AC units will there be in the country in the coming decades. So that was the first step to project the relevant drivers. Now we want to understand how much service will be demanded by each cooling equipment. And this is a service demand intensity that will reflect how much a household wants to use its AC units. And here, what we will do is look at what has been the growth rate in the past. So it's been a 4% year-to-year increase, and we will apply the same in the future. We can then deduct the total service demand because this was an information per AC units, and we had a number of AC units in the country. So we can see how total service demand expressed in terawatt hour it would be to evolve in the country over time. Once this being done, the next step is to look what the efficiency level have been and will be based on the allocation of technologies. So we were given the electricity demand in the country for this residential scope and for cooling needs. And we also have calculated what the total service demand have been, so we can deduct the efficiency level. And we can also get we were also given the historical market share of the past period. So with all the parameters, we will be able to make projections on the future efficiency. Again, we are taking some assumptions. You are saying that in the future, technology number 3, which would be a new technology. Let's imagine it's a very efficient AC units type of AC units, and there is some strong incentive from the government to promote those devices because they are more efficient. So the government could develop a policy and set a target of having this type of devices reaching 7.5% market share by 2030. And we could also have other policy supporting technology number 2, which is also quite efficient and having it rise per 1% per year. Technology number 1 will take the remain part. And this being calculated, we can deduct what is the efficiency of each technology is, and then what is the average efficiency. So we know what is the service demand, total service demand for AC units. We know the efficiency of the portfolio of devices which provide AC units. We can deduct what is the electricity demand for providing cooling services in the residential sector. So I've been a bit fast, but I want to hand over quick to Ariane and to Q&A. Maybe just to show that, as always, we can try to put on some charts and figures the results we just got from our modeling, and we can make some sensitivities analysis and build different cases. So I think you were asked, what if the future energy demand increases faster than expected? So we took the assumption that service demand intensity, so the level of service people want from AC equipments, go from 3.5% to 5% to 4% or to 5%. So we would see impact on those charts. Of course, this would mean higher demand, higher electricity demand. it can be this growth in service can be offset if we have more efficient appliances. And in that case, if there are policies that support even more technology number 3, which is the most efficient, if we aim that technology number 3 gets not 7%, but 20% of the market share by 2030, this would limit this would increase the overall efficiency, and this would limit the total energy demand. So I'm stopping here and now giving the floor to you, and happy to hear from any question you may have. And I'm looking at the Q&A box because there are already some very interesting questions.
Hello, everyone.
Thanks for joining us again for last part of this webinar with Zambia with Q&A.
My pleasure. Can you hear me well?
Yes, yes, very well.
Perfect.
So to all participants, feel free to raise your hand or to continue asking questions using the Q&A box. Ariane, I think you have seen some of the questions already asked. Would you like to comment some of them or to bring some specific elements?
Yes, so for the question of household occupancy, so what we do for the modeling is that we use really average household occupancy divided between rural and in urban, as Arnaud mentioned it. But so in our process, we don't take this stochastic nature into account, but of course, if you have more precise data about this, it's always better to include this in the modeling. But for now, we don't have enough details at hand to include this in our modeling.
Yes, that's also what I answered. Just to stress that whatever data you have, if you are aware of any work in Zambia or neighboring countries or in the region, that can help us refine and make our modeling exercise more accurate. We are very, very happy to discuss it with you and to improve and to make it more disaggregated and detailed.
There was a second question about energy indicators. So I don't know exactly to which type of energy indicators the question is referring to, but the idea behind the energy indicators is, of course, to have energy indicators that are relevant to the regions that we are modeling. So if we don't have data, we will use, of course, data coming from other similar regions, for instance, or average data. So of course, we will lose a little bit of information. But yeah, so the more data we have to compute these energy indicators, the better the modeling will be. And
I'm just coming, Ariane, because the question was asking before the second part of the presentation, where this slide was commented by Tim, where you just to stress that we have been able to get some data with rural urban breakdown on the household appliances ownership rate, for example. So this is just one example where we could break down between urban and rural and make specific projections on those parameters. But again, we are all hungry for data, to make our model more accurate. So if you're
Exactly.
aware of any other sources, we're always happy to take them into account.
And so for trend of cost of pressure cookers and biogas-based gas stoves, I don't have them at hand, but some of our assumptions are available in the public documentation of the model. But I'm not sure this specific data are public. But of course, we assume evolution of costs for these two types of technologies, and we can see later with Arno if we can share some data regarding these technologies.
And I don't know, Ariane, if it's worth mentioning our another team with whom we are working a lot. They are called ETP, really looking at ETP standing for Energy Technology Perspective, who are doing a lot of modeling on what the portfolio of technologies could be in the future, what will be their cost, their prevalence. So we are working a lot with them, and they're really looking at innovation of all the equipments. In the case of cooking, I don't know how far they have been in looking at pressurized electric cookers or biogas based gas stoves, but of course they have some prices assumption. I don't know, Ariane, if you've been discussing that with them.
Yes, we've discussed this a lot with ETP. Unfortunately, they don't have more data than us about this specific part of the modeling, but it's definitely one area where we would like to improve our database, our modeling process. So any information is, of course, welcome. But for now, the different technologies that we have, we can discuss if we can share some data related to these ones.
Perfect, thank you. And maybe it's just to mention something else on the electric pressure cooker. There is one other angle we're working on. That is we are working, for example, with the government of Morocco and of Indonesia, who have been heavily subsidizing LPG, which has been a very good fuel to see people move away from the traditional use of biomass to modern fuel, but this has entailed issues because it's heavily subsidized and it's weighing a lot on the it's a burden on the public finance of the government. So they are doing a lot of work to see if people could shift to electric cooking devices. And one angle which is explored and studied, it's not about cost, it's more about social acceptance. Like, can you cook traditional Moroccan dishes not with gas and not with flame, but with pressurized cookers? Can you have people move from one device to another one, depending on the type of recipe they have, depending on the type of dish they have? So this is a very different angle on seeing how the different portfolio of cooking solutions could be allocated to people, more based on habits and appropriation.
Yes, indeed. So I don't know if you mentioned this before, but of course we have a lot of different technologies that are available in the model, and not only LPG and biogas stoves, but as you mentioned, also electricity cookers, improved biomass cook stoves, etc. So the portfolio is quite large already, but it's always better to improve it. And there was also a bunch of questions around urban building energy modeling. So there was one question about local weather data. So of course at the IEA we're not doing projection of weather. We rely on other organizations that produce this kind of weather forecasts. But we use it to inform our modeling. Of course, the better the disaggregation is, the better we can inform, we can assess the impact of weather on the energy demand. And of course, with the climate change, the impact of weather will have a strong impact on the energy demand, for instance, cooling. So this is one of the parameters that we used to do the projections of energy service demand that in the end will have an impact on the level of total final energy demand. I don't know if it was the original question about this, if I answered it correctly.
Yeah, so Mr. Joshua, if you want to raise your hand and take the floor to elaborate more on what you know on urban building energy modeling, and it sounds like you have some experience on that, so you feel free to speak up about it. I don't want to put spotlight on you, but just in case you feel like you want to speak, just raise your hand, and we are happy to have a discussion on this specific urban building energy modeling tools and approach.
Maybe a quick note on how we do this type of modeling in the Rio. It's as mentioned by Arno in the presentation. So we split urban and rural areas, but we don't have the capacity to really do details modeling per country, for instance. So we stay at the level of region, and yeah, we try to incorporate as much as possible the data specific data for rural regions and for urban areas, and yeah. And of course, yes, the total must match the region energy balance. So that's also one way of checking if our split is working or not.
Okay, thank you, Ariane, and thanks again, Mr. Joshua, for those questions. We still have a couple of minutes, so if there are any other questions, we're happy to answer, be it on the Excel exercise or on the presentation itself. And if not, I don't know, Ariane, if you don't know if you have any other information you would like to share. Maybe saying a word on the ongoing work on the net zero and what does that entail for the building sector. I've presented a bit this new piece of analysis to our participants from Zambia and from the Southern Africa region. But I don't know, maybe if you want to, without disclosing some results, because the report will be out in a few weeks.
Sure, sure. So so the NZD report will look at pathways for the global energy system that reach the net zero carbon goal in order to respect the targets of the Paris Agreement. So of course it's really ambitious for all the sectors. And for buildings, it means, of course, a lot of changes. So, for instance, what we try to underline in our report, it's first that the building sector needs to implement more stringent building energy codes, retrofits for existing buildings if needed. So that will allow to decrease the level of energy service demand, or to to lower the increase of the energy service demand, because of course in some regions there will still be an important growth in the energy service demand. Of course, we need to work on the envelopes of the buildings, but also need to change the technologies that are used in the buildings. So it means that we need to rely more on more efficient appliances, that we need to use more heat pumps for heat, more efficient ACs for cooling, and that will allow us to decrease the CO2 emissions linked to the building sector. Of course, in some regions, the building sector cannot be completely decarbonized, but it will rely as much as possible on other low carbon fuels. And finally, our scenario still, of course, meets the goals of the Sustainable Development Goals. So, of course, we still have 100% clean cooking access for everyone by 2030. A few points from our NZD reports, but more details are coming soon.
Thank you very much, Ariane, and we'll have a specific presentation of this report in the coming months for our participant to this training with Zambia, but also with other countries. So just stay tuned, as we'll be happy to provide more information very soon. Okay, I don't see any more questions, so I would like to thank you, Ariane, for your participation. Also thanking Tim, who commented a few slides and parts of this presentation. I'd like to thank you, all of you participants, for your participation and attention on this topic. And tomorrow at the same time, so 9 a.m. Lusaka time, we will meet again for a new session on energy modeling. After having looked today at one end-use sector, that was building, tomorrow we will look at the power sector with all the implication for doing some modeling and projecting how the power system is to evolve with the management of installed capacity, how will that meet electricity demand, how to integrate renewable sources in the mix of generation, and we'll also discuss several topics like price and LCOE. So we'll be very happy to share our perspective on that, and to share also a bit of our findings and results of our modeling exercise on the power sector for Africa. So thank you, Ariane. Thanks to everyone, and talk to you tomorrow morning.
Thanks a lot. Have a nice day, all.
Bye-bye.
Bye.